Hi there, this is Mrs. Often, and in this lesson, we're going to review theorems about perpendicular and angle bisectors and their connections with isosceles triangles. So the objectives of this lesson is that by the end of this lesson, you will be able to apply theorems about perpendicular bisectors and be able to apply theorems about angle bisectors. Both of these will be used to find various important centers of triangles, and we'll be using them in a project later this term. Please note that this is a video about some theorems that we actually already proved, and that this slide deck goes on beyond these videos. That information covered, however, is about writing the equation of a perpendicular bisector, something that we've already talked about. So you should review that information just as a refresher on this topic. So let's get started. So an important vocabulary word here is equidistant. And when a point is equidistant, then it is the same distance from two or more objects. Now, those objects could be other points, it could be lines um, in space. So we can use triangle congruence theorems to prove theorems about equidistant points. And that's what we did when we proved those angle bisector theorems and perpendicular bisector theorems as we were working through our unit on congruent triangles. So again, these two important theorems and their converses relate to perpendicular bisectors of segments and angle bisectors, and we used properties of congruent triangles and CPCTC to prove them. So perpendicular bisector theorem, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So we can see that X lies on that perpendicular bisector. XY is in fact the perpendicular bisector of segment AB. We have YA congruent to YB and XY perpendicular to AB. So that's really the definition of something being a perpendicular bisector. Our conclusion, therefore, is that XA is congruent to XB. Now, we also work to prove this converse, and we showed that when XA is congruent to XB, that necessarily this had to be the conclusion. So we're going to use this, but first I just want to introduce another new term, and that is locus. So a locus is a set of points that satisfies a given condition. For example, a circle can be defined using locus by saying it is the set of all points that are equidistant from a common point called the center of the circle. All of the points on the circle are the radius distance away from the center. So the perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of the segment. And that comes from the perpendicular bisector theorem that we just introduced. This is therefore slightly different from that definition of perpendicular bisector, that it is the segment or line or ray that divides a segment into two congruent smaller segments and is perpendicular to a segment at the point which is defined as the midpoint. So here the locus definition is just a little bit different. And please don't confuse this with that destroyer of crops, the locust. So here's an example. Now in this diagram, we see that DG is 36.4, EG is also 36.4, and DE is 20.8. So we are additionally given this information that GF is perpendicular to segment DE. Now, since G is on this line, GF, and it is equidistant from the endpoints of the segment, the converse of the perpendicular bisector theorem tells me that these two segments, DF and DE, must be congruent to each other. So here I'm using the converse of the theorem. I know DE has got to be twice the length of EF. Since DE is 20.8, I can substitute, and then I can use the division property of equality to determine the measure of EF. Now again, we can use this method because we know that GF is the perpendicular bisector because we are given that right angle. What if we don't know that GFE is a right angle? Well, in that case, we need to be given some other information. For example, we need to be told line L is the perpendicular bisector of DE. We need to be told DF is congruent to FE. We need to be told that F is the midpoint, for example, of the segment. So something like that, so that we're going to be able to get to the perpendicular bisector of the segment. And then to find that length of EF. So please be careful, because if this is not perpendicular, if it's just G connecting to some point somewhere along DE, then we can't make that assumption. If this is not a right angle, that's going to be the case. Okay. So another thing that they could tell you is that the distance between point G and DE is measured along line GF, because then that's also going to tell us that it's perpendicular, because the distance between a point and a line is defined as the length of the perpendicular segment from the point to the line. Okay, so this example is a little bit more challenging. It is going to involve some factoring. Note again, we are given that UW is the perpendicular bisector of segment TV. So we're going to begin by saying, well, with the perpendicular bisector theorem, TU has got to be congruent to UV, and we'll substitute in those given values. We're going to subtract 7x on both sides, so we'll get a quadratic equal to 0, and then we'll factor that. So please be careful when you're factoring. Note that this middle term is -7, and that this final constant term is -6. You want to have different signs here for 2 and 3. So we get a negative answer when multiplying, and we want it to be -3 so that we get -7 when we add. We'll factor, we're going to solve, and you'll notice that I get x equals -2/3. Well, -2/3 is not going to work out here. I do want to see that you've solved and you've listed both answers, but be sure to tell me that the first solution is extraneous. It's going to produce a negative value for UV, quite obvious. We need a positive value there. TU is 21 and VU is also 21. Okay, our next theorem is the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. And we can see this here, that what we have is angle-side congruence, and therefore CB must be congruent to CA, or as they listed here, AC must be congruent to BC. In the converse of the angle bisector theorem, this proof is actually pretty easy to do. It's a hypotenuse leg proof, and then by CP/CTC, we get that APC is congruent to BPC, and therefore, since their sum is equal to the angle APB, we can use substitution to demonstrate that one angle is APC, or BPC is half the measure of the full angle APB, and therefore PC is the angle bisector. So again, looking at the angle bisector as a locus of points, So it is the locus of all points in the interior of the angle. So here we're looking at a ray that is passing through the interior of the angle, and all those points are equidistant from the sides of the angle. Remember, we are measuring distance along the perpendicular to the side of the angle. So a couple of problems here. Finding the measure of BC and justifying, well, pretty obvious here. What we have going on is an angle bisector. We know CD is 7.2 units. BC and DC must be equal by the angle bisector theorem. We substitute, and therefore BC is equal to 7.2. Now, applying the angle bisector theorem, we notice here again, we have the measure of MKL that we are being asked to find, not the value of A. So please be careful. Don't just find the value of A. By the converse of the angle bisector theorem, we know that JKM and LKM must be congruent. Therefore, their measures must be equal. And so I'm going to substitute my angle measures, and I'm going to solve to get A is equal to 6. Now, by substitution, I will get that either one of these angle measures is going to be 38 degrees. And I can use that also to check my work. I do want to make sure that both of them are equal to 38 degrees, but they are specifically asking for the measure of MKL. Here we have another example of an angle bisector theorem. XY or XW and ZW both have the same measure, and therefore we have congruent triangles by, again, hypotenuse leg. That tells me that XY and YZ have to both be congruent, and therefore WYZ and WYX must be equal to each other. So we'll walk through this. WYZ plus WYX is equal to XYZ. That's the angle that we're trying to find the measure of. So by the angle bisector theorem, WYZ is equal to WYX. I will substitute. I could also have used half angle bisector here instead of substitution. Looks just a little bit different. Instead of saying 2 times the measure of WYZ equals the measure of XYZ, remember that half angle bisector theorem would be saying that half the measure of XYZ is equal to the measure of WYZ. I am going to get the same answer either way. After substituting 63, I will get that 126 is the measure of angle XYZ. Okay, an application here. We have a spotlight. It's being hung along the back of a display case. I'm sorry, in this presentation, my segment labels have moved over a little bit, so they're not wearing their hats correctly. We see wires AD and CD are the same length, and A and C are equidistant from B. Now, we could do this with congruent triangles. How do the wires keep the spotlight centered? Well, we can look at this, that AD is equal to CD. That means that D is on the perpendicular bisector of AC, because we know that it is equidistant from the endpoints of the segment. And since B is on the perpendicular bisector as well, it's got to be the midpoint. So BD is the perpendicular bisector, and that means that even if we were to extend this, the spotlight would be centered under that mounting. It would always be equidistant from A and C. So that's an example for you. Again, a reminder that the rest of this slide deck, which is available in the Google Classroom, should be reviewed so that you have a quick refresher on how to write the equations of perpendicular bisectors of segments. Thanks so much, and be well.